So first off, thank you for being here and visiting us.
Thank you.
Before ATS, I know it's a lot of travel before ATS. So it's really a pleasure for us to have Professor Matthew Juniper here from Cambridge. So he's one of the world's foremost leaders in fluid mechanics, and in particular, a pioneer of applying Bayesian methods to these kinds of physical inference problems, especially in fluid mechanics. He has a very illustrious career, lots of awards. I'm not going to take his time to tell you all about him, but I hope you all get a chance to meet him after his seminar. I think that's going to be the most valuable for you, is to spend some time actually getting to know Matthew while he's here. Without further ado, thank you so much for being here.
Well, thank you. And it's customary to say thank you for inviting me, but you didn't. I totally invited myself. So thank you very much for letting me come and talk. It's very nice to meet you all. I'm actually free all day, so there's sort of meetings till 3:30. I'm very happy to stay longer. And then flying to Washington tomorrow at 8 a.m. So very relaxed. It's a great pleasure to be here. There really is something relaxed about the west coast of the US, which I really like. So it's very good to be here. Just a bit of history. I'm going to this is a rather dry title, Adjoint Accelerated Bayesian Inference. Bayesian inference, I'll talk about. Adjoint accelerated, I'll talk about. I think they're really important things to know about. And what I'm struck by is, in the machine learning community, it feels like not many people are aware of the speed up you can get with adjoints. And in the fluid mechanics community, we aren't really so aware of Bayesian inference. And when you put the two together, they're super powerful. Is this all right, Sam?
Are you recording, Sam? Yeah.
And so this is what I want to talk about. Like there's no new idea under the sun. These are just ideas brought together. And if you were to hunt around in the area of probabilistic programming, programmable inference, you'll find in the sort of, the geekiest corners of SciAm, for example, you'll find these sorts of ideas, but often applied to rather simple toy problems. And what I want to show is how you can apply them to these much bigger problems. So that's really where this came from. And I'm a bit unusual. I sort of an experimental PhD, big experiments where they were about half the time not working. So I got to do a lot of theory while the things weren't working. Went and did flow and stability in a theory sort of world, but also always kept a little experimental rig in my lab. And that I think experiments keep you honest, because they force you to confront the fact that your models, while they may look perfect, aren't always perfect. And then as time has evolved with this experimental lab, we've started getting, it started off everything by hand, you get 100 data points. Now everything's automated, you can get 100,000 data points, even 1 million data points. And then you have to look at data differently. You have to say, what information is in my data and how do I extract it? And that's, I think, the thesis, the core of this talk is, how do you extract information from data? And of course, it coincides with lots of work being done in neural networks. And my sort of deep sense of unease at the fact I think people are overusing neural networks. I don't think that's actually that controversial, but in some worlds that is controversial to say. And so I want to talk about other ways you can achieve the same thing without a neural network, and I think in a rather better way, certainly a more satisfying way, by keeping physics in a model rather than using physics agnostic models. So what I want to do is start with a bit of philosophy, physics, modeling, analysis, then an introduction to Bayesian inference, and then I'm going to show an example of polynomials. And everyone knows what a polynomial is, but it gets the idea across in a very visual way that you'll be able to picture. And that'll actually take about half an hour. So that's the introduction to the sort of basics. And then underneath some examples. I'm very happy to take questions. And if we start overrunning, this whole thing will take about an hour. If we start to overrun, I'm happy to skip stuff. So just leave that to me. If you have any questions, do ask. Anyway, here we go. Bit of philosophy. Here we go. So physics, which is what the world does. Modeling is how we model what the world does. So we look at what the world's doing and extract what we think is important from it. So here, for example, is the period of a pendulum. T is 2 pi root L upon G. There's a model. It's been based on small angle approximation. It's neglected wind resistance and so on, but it's kept in the gravitational force. So we've extracted something important from the physics, and that's what we're modeling. And then analysis is the maths we do on the model. So if you go to a maths department, all they do is analysis on the model. Physicists will tend to do mainly sort of physics and maths, and engineers do everything, all three. Now that's a physics-based model. These days, of course, you have access to these physics agnostic models, neural networks where you'll take some inputs, then you have weights and biases and some outputs. So whereas this physics-based model has one parameter, if you look upon it as mapping from L, the length, to T, the period, the parameter is G. A physics-agnostic model will have possibly millions of parameters. They'll be the weights and biases of the neural network, but ultimately it's still a model. And even though we say it's physics agnostic, it's not an agnostic model. By creating a neural network in a certain way with a certain number of layers and nodes per layer, you actually have incorporated some hard constraints into that neural network. And I think people sometimes forget that. A neural network is not a totally malleable thing. With the hyperparameters, you have constrained the outputs that it can give you as a function of the inputs. Anyway, then the analysis I've sort of split here into sort of four elements. Firstly, tuning model parameters to assimilate data from experiments. You'll have done this at school. Certainly in British schools, this is what you do for that very model. You would measure a pendulum, length 1 meter, measure the period with a stopwatch, period 2 seconds, and then back out G, gravitational acceleration, roughly 10 meters per second squared. So that's a very typical experiment you do in a school. If you had a good physics teacher, they'd have said, now, measure it again and put an uncertainty on that. So it'll be 1 meter plus or minus 1 millimeter. Measure the period, 2 seconds plus or minus 0.1 seconds. And then you can back out G and the uncertainty in G. So that's a sort of second level of analysis there. Now let's imagine you had a bunch of measurements from a pendulum where some of them were at large angles. You'd find the model there isn't terribly good. You won't be able to assimilate all the data into that model. You'll get different values of G because for the large angles, that small angle approximation breaks down. So what you could do instead is say there's another model I can introduce here that has theta 0, which is the angle of the oscillation. And there are many correction terms which I haven't put in there. So this second model here, the period now is a function of 2 pi root L upon G times something that contains the angle of oscillation, which is large. And that's a better model for modeling these large angle oscillations. So if you have a lot of data, you could say, I can fit that data with 2 parameters, which are G and theta 0, much better than with just one parameter, G. So then you say that second model is better than the first one. The data has more evidence for the second model than the first. Now that's something that's very rarely taught in schools, even at undergraduate level, but is the sort of essence of what I'm going to talk about today. So you compare these models and say that one's better than that one. But it's worth dwelling on something now. Those two models are just two ways of describing the data. If you only have data taken at small angles, then that first model is better because you can match the data with one parameter instead of with 2. And actually, there's no information in the data about that second parameter, so you couldn't assimilate it anyway. So it's worth bearing that in mind, that models, you want them to be as simple as possible, but that match the data. And you can codify that with Bayesian inferences, I'll show later. And it's worth just thinking about what that physics agnostic model would do, the neural network. You could train it to get T the period given L the length of the pendulum on lots and lots of data, and it would work fine on Earth. But were you to go to the moon or to Mars, it has no information, of course, inside it about G, the changes in G, whereas the physics model is somewhat better because you can extrapolate if you have knowledge about G. So if this is a case where the physics-based model is clearly better than the neural network because it can extrapolate to other planets if you want it to. So in this talk, I'll show 2 physics-based models. One is a reduced order thermoacoustic model with roughly 10 parameters, order 10, it's more like 15. And then secondly, a Navier-Stokes boundary value problem, which in 2D has roughly 10,000 parameters and in 3D has of order 100,000 parameters. So I'll show those examples there. And I actually won't show any neural networks in this talk, but about in the last sort of 3 years, about half my papers have involved neural networks. So it's not like I don't use them. It's just that I want to be careful about when I use them. Okay, Bayesian inference. Now, you might know this, Steve. This is Steve's paper on machine learning for fluid mechanics, which I've read a few times, but I just want to highlight one bit of it. The important topics we've not covered, Bayesian inference. And Steve, you wrote this: every machine learning framework can be cast in a Bayesian framework. And actually, I think the natural framework is Bayesian for machine learning. But it may be argued that Bayesian inference may be more powerful than machine learning because it provides probability distributions for parameters, leading to robust predictions rather than single values. And I quite agree with that. But it's very expensive. A key drawback is its computational cost because it involves sampling and integrating in high-dimensional spaces, which it does when you do it really rigorously. But what I want to show is that when you bring in adjoints, that limitation disappears. Suddenly you can assimilate data very, very quickly. And so you have to make one assumption, and I'll talk about that assumption. And you have to remember that you've made that assumption because otherwise it won't work. But I'll come to that next. First of all, though, back to, I think, what you call in the States 101. Conditional probability 101. Here we go. Trivial statement. You ready? The probability of A given D is equal to the probability of A the probability of A and D together is the probability of A given D times the probability of D. And that's equal to the probability of D given A times the probability of A. Trivial statement, which we're now going to give meaning to by giving meanings to A and D. So you have to imagine this. Now, I don't know whether this is going to work in the States, but we'll soon find out. It works in the UK and it works in Europe. You're driving along what we call the motorway. You call that the freeway, don't you? The freeway at the speed limit, possibly a bit beyond. You look in your rear view mirror and you see this. That's car's headlights flashing like this. What is the probability that that car is an Audi? Does that work in the US? What would it be? In the UK, it's an Audi. What is it in the US? Someone said a Tesla once. A Bimmer. Yeah. Yeah. Okay. A BMW. So what's the probability? So how do you work this out? Well, you have to introduce some prior knowledge, and that's what Bayesian inference does. You say what your prior knowledge is and your confidence in that prior knowledge. So this is a British Audi. This is a typical Audi driver in the UK. You can see him there, sitting there in his white shirt, on the other side, by the way, from the one you're used to, but doing what they do best, which is basically drive around as if they, no one else matters. So there's your Audi driver. Now let's go back to this, and I've just rearranged the two right-hand things here. So we've got the probability of the car as an Audi, given that it's driving too close. That's what we want to work out. Is equal to the probability that it's driving too close, given that it's an Audi. Now that's clearly 100%, times the probability it's an Audi, which if you look around the code is about 1 in 10 in the UK, divided by the probability that it's driving too close. Now, if all Audis drove too close and nothing but Audis drove too close, then all the cars driving too close would be Audis, and so these two would cancel out, and this would be 100%. But if there are some BMW drivers, they don't want to feel left out. They'll be driving too close as well. And that means that the probability the car is an Audi is a bit less than the probability it's driving too close because of the extra BMW drivers. So you can see that the probability it's an Audi given it's driving too close is now a bit less than what we had before.
Saying that most people drive too close in the UK.
In the UK, a lot of people drive quite close. You should go to France, and then it's like, this is 1 on the bottom, and then I don't know what happens then. You've got no more information, right. Basically. That's actually what it is. If every car is driving too close, then you have no more information from P of D given A. So, but this is just a sort of silly point to say, the whole point of Bayesian inference is that it provides a framework within which you can bring things you already know to bear on a problem. Now, what I'll do today is to give slightly different meanings to A. Imagine we've got a model like the one I had for the period of a pendulum, which has some parameters. In that case, it was G, the gravitational acceleration, but I'll just label the parameters A, and there can be any number of parameters. D is data from experiments. S and C I'll come on to later. What we have now is we want to work out, given some data, what are the most likely parameter values of our model. So for the pendulum, for example, we've got some measures of L, we've got some measures of T, the period, that's what I call the data. And given that data, we want to work out the most likely value of G, the gravitational acceleration, or in fact, the most likely value, but also the probability distribution. That's what we want to work out. And that's equal to this term here. Now, if we're just trying to find the most likely value of the parameters, we just have to maximize this numerator here because the denominator doesn't depend on the parameters. So we want to maximize the denominator here. And this is 2 probability distributions multiplied together. This is the prior probability of the model parameters. And this is what's called the likelihood. Think of it as the probability of the data given the parameters in the model. It doesn't have to sum to 1, so it's called a likelihood rather than a probability. But what I'm going to do now is just make 2 assumptions. Firstly, the prior distribution is Gaussian, and that's fine. You can impose that. But then this is the really crucial assumption. We're going to assume that this probability distribution of the data given the parameters and the model is also Gaussian. Now that's not true. It's true in one special case. It's true if you have a linear model and your prior probability distribution is Gaussian. Then this will, and if your measurement noise is Gaussian as well, then this will be Gaussian. But if your model is nonlinear, and most of them are, and if your measurement noise is not Gaussian, which is sometimes true, then this will be a stretch. This is a sort of an assumption that is not always true, but you can always check it afterwards. So the argument I make is it's worth making this assumption now, early on, because you can check it later to see whether it's right. And if you make this assumption, everything gets much faster because you can use adjoints. So that's the assumption that you make early on, and you have to remember you've made it and go back and check it afterwards. Now, if these two are Gaussian, then this is Gaussian as well, and I'll come back to that in just a minute. So now I'll think about how do we express the probability of the prior model parameters. So I've got my model, which may have 4 parameters, and I'm going to say, I know each of those parameters, I know the expected value and the variance of each parameter. So I get a multivariate Gaussian distribution, which looks like this. The probability of A is proportional to an exponential of -1/2. I've missed out the half just for ease of presentation. And then it's a discrepancy. There's a general value of A, the prior value of A. I have some discrepancy between the two, multiplied by some number, which is the certainty I have in A, or the inverse of the variance of A, that discrepancy, and then multiplied by itself. So this is a sort of sum of squares in the argument. And in matrix form, it would look like this. So I've got 4 parameters. I look at the discrepancy between A, the actual parameter value, and AP, its prior value. Multiply it by, if I just look at the first one, multiply it by the top left corner of this matrix, multiplied by itself. So it's the discrepancy squared times some weighting. And that prior weighting has 4 different ways of thinking about it. Think of it as the prior weighting given to parameter 1, the prior certainty, the inverse prior uncertainty, or the inverse prior variance. These are all equivalent ways of saying what that top left corner of that matrix is. And if you know nothing about your parameters before you start, this prior matrix is probably diagonal. You're just saying I'm putting inverse variance on the diagonal. But as you assimilate data into a model, you'll find that the posterior starts to become a full matrix. That's because some uncertainties are correlated in some parameters, are correlated to the uncertainties in other parameters. So this can be a full matrix as well. And indeed, as you sequentially assimilate information, it probably is a full matrix, because uncertainties in one parameter are really dependent on uncertainties in another parameter as well. It's indeed a very good experiment where all your experimental uncertainties remain uncorrelated in all the parameters. What's that? Just a bell. Okay. Okay, so that's what the prior distribution of parameters would look like, the P of A. And I'll turn attention to the probability of the data given the parameters. I'm being a bit loose with the language, but it doesn't really matter. So what we assume now is that that model is a perfect model of the data. This is an assumption, but the data has been corrupted by Gaussian noise. That's what we're assuming now. So we say the model prediction S is a function of the parameters A, and this is a prediction of the thing we're measuring. So I take the discrepancy between that and the data, I multiply it by some certainty, and multiply it by itself. So this is adding together sort of squared discrepancy between the data and the model multiplied by this red thing, which is, again, it's rather like what we had before. It's a certainty you have in that particular measurement, which is also the inverse prior uncertainty or the inverse prior variance. So this is, if you have measurement noise, this is the inverse of the variance of the measurement noise. So that's something, again, you have to impose. So at all points you've said, I've got my prior certainty in the parameters, which I've expressed in terms of the variances of my parameters when I start. I'm now I have to say what the measurement noise is. And only then can I assimilate the data to get the most likely model parameters, P of A given D.
That certainty is of the model prediction minus the data.
It's actually, that's, the certainty here is the measurement noise.
Right.
And this is a subtle point, but we have to, well, you have to lump together in the way I've done this here, model error with measurement noise. Now, the way I do that is to say, we'll assume the model is perfect and say there's some discrepancy in the measurement, some mistake in the measurement noise that contains systematic measurement error, but also contains model error. So we're not distinguishing between these two. That's very, very hard. So I actually tend to think of systematic measurement uncertainty as being just like model uncertainty, because there's something in your model you haven't modeled, which is the systematic error in the measurement. And I'm now jumping to sort of the end of this. The unknown unknowns, systematic measurement error you don't know about. That's what kills you in experiments. It's really hard to deal with. But I lump it into model error. Or, you know, say that I don't try and distinguish between the two.
What is the subscript for?
Good question. Experimental error, let's call it that. These were taken from a particular paper I wrote where it was defined. I can't remember quite what it was. But yeah. So it's worth thinking about how you do this practically, because as ever, it's the practical implementation that is often harder than the idea itself. So I'm going to show some experiments which are from an acoustics rig. And what we do is sorry, I'm going to go back. These are Gaussian, the numerators are Gaussian. So if I multiply them together, I get the product of two Gaussians. If I take the log of that, I get the sum of the arguments of the Gaussians. And then I'll do the negative log of that just to make something I'm going to minimize. So I define J to be the negative log of the numerator that I just had. So that means I get J is this cost function, is the sum of the arguments of the Gaussians. So typically you'd have this, the prior estimate of the parameters, which is what we had before in the argument for the multivariate Gaussian for the prior. And then you've got a growth, and this is an acoustic problem, you've got a growth or decay rate of acoustic oscillations, which is ZR. You've got a model prediction, SR, the discrepancy between the two multiplied by the certainty in the growth or decay rate squared, that's multiplied by itself. And then we've got a frequency. So again, we take the discrepancy between the model prediction and the measured frequency, square it and multiply it by the certainty. And then we have a set of microphone pressure measurements, and we look at the relative pressures of microphone 1 to a reference microphone, etc. It's in the frequency domains, there's a real and imaginary part, but you end up with this cost function for each microphone, and that's for every operating point. This is the practical implementation of this. The point being, you end up with this enormous cost function, J, that has many, many terms, but is very easy to code because it's in the loop. So that's how you're going to assimilate the data. And so we might have, we've done this for 100,000 operating points, and at each operating point you have about 10 measurements, so you've got about 1 million elements to this cost function. And that's fine, because it's in the loop. Right. But what we want to do is find A, the parameter values, that minimize J, which is the same as maximizing the numerator of what I had before, the posterior probability distribution. Now that, you could do that with a non-gradient-based optimization method, but it would take a long time. It's far easier to use a gradient-based optimization, but you can see for that, you need the gradient of the model predictions with respect to the parameters. And that's inside the model. You have the model, so you have the outputs, the model predictions as a function of the parameters, but you need to differentiate it. And that's where the adjoints come in, because adjoints give you a very robust way to get the gradient of the model predictions with respect to the parameters of the model. So that's what I call here ds by dai, dp by dai. Once you have those, you get dj by dai for all the parameters, I is 1 to whatever. And now you can use gradient-based optimization to find the parameter values that minimize this cost function, which maximize the probability. Now, this is not a new idea. It's called 40 var in some areas. But nonetheless, the point is you use the adjoints to get the gradient information so that you can do this very, very quickly. So that's the first way you use adjoints, and that's nothing particularly new. In fact, none of this is particularly new. It's just what I'm proposing to do is at vast scale instead of these small toy problems. But the next thing is this. What I've done now is say, we're going to compare various models against each other. So HI is hypothesis 1, 2, 3, 4, up to whatever number you like. Let's say 10 hypotheses, HI. And so this is my prior probability distribution of the parameters given each model. So each model will have different parameters. This is the same as before, but explicitly saying where the models appear. Now, if these two are Gaussian on the numerator, then this posterior probability distribution is also a Gaussian. And that means that it can be expressed as the negative log of that is simply A minus the maximum A posteriori, that's the most likely parameters, the discrepancy between a general parameter value and the map point, the maximum, the most likely parameter values, squared, multiplied by this matrix, which is this posterior covariance matrix. This contains all the uncertainty in the parameters after you've assimilated the data, if it's a Gaussian distribution. Now, this is simply the second derivative of J, cost function I was showing 2 slides ago, with respect to pairs of parameters. Now, that is an unfeasibly difficult thing to calculate if you're using finite difference with lots of parameters. But with adjoint methods, it's expensive, but it's totally tractable. It scales with n, the number of parameters. So it's not actually that many calculations. So to get this posterior covariance matrix, you need the first derivatives, which you have already, of the model output with respect to the parameters. And you need the second derivatives with respect to pairs of parameters, which is not a lot to calculate for a model with a few dozen parameters, or even 100 parameters. It's only 100 calculations. So it's perfectly sort of tractable. But I would say this is just a little tip. This second derivative here, it mainly comes from the first derivatives. This is called the Gauss-Newton approximation. And the second derivatives just add a little correction, about a 10% correction in our acoustics case. So you can get away without calculating them. And if you've used an optimization method like BFGS and it's done a few hundred evaluations, and let's say you've got 10 parameters in your model, it will have worked out an approximate Hessian, this is what this is, as it does the optimization. And you can often use that as well. So this bit here, I mean, using the second derivatives gives you the perfect answer for this matrix A, but often just using the first derivatives gives you a very good answer. So you can often stop there. Right, so that's how we get the posterior covariance matrix with the second order adjoints, but usually the first order is enough. It doesn't stop there. What we really want to do is to compare models against each other. So what we want is the probability, or the likelihood, I should say, of each model given the data. So think back to the pendulum. You've got the small angle approximation and the big angle approximation. We want to work out, given this data we have, which model is most likely. Now that, using Bayes' rule, is just the probability of the data given the model times the probability of the model with some proportionality. And if I have 2 models or 10, let's say I have 10 models, and I don't know which of them is the best, I assign a probability of 1 in 10 to each of them before I start. And then finding this just comes down to finding the probability of the data given the model. And that is actually just found by integrating that posterior Gaussian distribution with respect to all the parameters. So I'm going to integrate over parameter space of the thing I know already. Now, this is what, in Steve's paper, this is what's very, very expensive, unless your probability distributions are Gaussian, in which case it's trivially cheap. Because this probability distribution here, this integral, is just the peak of the posterior likelihood, which you've already calculated, times the determinant of the matrix divided by 2 pi to the power of a half. And that's, again, this might be, even if that's like a 200 by 200 matrix, that's milliseconds of calculation. It's very, very cheap. And what this does, this is interesting, this penalizes models that have too many parameters. So this, you can get, as we'll see in a minute with polynomials, and you know already, if you have 10 data points, you can fit a 9th order polynomial perfectly to those data points. But we'd all be a bit suspicious of a 9th order polynomial model going through 10 data points instinctively, because we know that if we got those coefficients slightly wrong, the model output would change a lot. So while the peak of the posterior likelihood might be quite high, in the sense that you can fit the data really well, because you've got too many parameters, this matrix will be very penalized by this term here. So this term penalizes models that have to be really carefully tuned to match the data, even if they match the data really well. So we'll see an example of that in the polynomials example in a minute. So that's what you get from the Bayesian approach that you don't get with the other approaches. So, Sam.
How are you handling the nonlinear dependence of the data on the parameters A? It seems like that P of D given A and the model would be nonlinear.
Well, the model can be nonlinear. And what I do is say, you accept the fact that you sort of hardwire, you assume, maybe that's the way to put it, you assume that the probability, this term here is Gaussian around the model prediction. But it is an assumption you have to test afterwards. So it's an assumption that allows the analysis to be quick, but it's not necessarily a good one. So you must go back afterwards and test it. But you have assumed in there that the model is at least around the point you're interested in. It's locally fairly linear. and that the measurement noise is Gaussian. That's really what you've assumed. But often that's true. With PDEs, with relatively smooth outputs, that's actually quite a good model. It would be bad for a very turbulent flow or a chaotic flow. The Lorentz problem, Lorentz 63, this would be bad. But you can check afterwards. Right. Okay, now for everything from now on is just pictures. You'll be pleased to hear. So polynomials, here we go. What line would you put through those data points? This is always a test of the audience, by the way. What line would you put through those data points? There are 10 points there. Go on, do this with your fingers. All right, I can tell that you're all numerical people. This is your CFD evangelist. You know, I've got my boundary conditions, I've got my equations in the middle, I've got my data, everything's perfect. This is what an experimentalist would do. In fact, frankly, an experimentalist, if they're feeling brave, would do that. If they're really jaded, it'll just be a horizontal line, you know, one number. So that's an experimentalist. The point being that when you look at that, there's something really important missing from that. What's missing, Steve? The error bars, absolutely. Error bars are missing. If I show you this is 2 standard deviations. Instinctively, what line do you put through those now? A straight line, possibly even a horizontal straight line. And if I show you that, you instinctively draw a wiggly line. Humans are really good at this game. We're really good in 2 dimensions at doing this game. The nice thing, though, is that you can make a computer as good as a human, but do it in n dimensions. Humans are very bad at anything more than 2 dimensions on this particular game. So what we'll do is this. We will take some points, exactly the same points, and I'll change the measurement noise. We will have models which are polynomials of order 1 to 9, and I'll maximize the likelihood. I'll find the parameter values, that is to say the polynomial coefficients, that fit the data best for first order, second order, third order, all the way up to 9th order polynomial. And I'll find the uncertainties in those polynomial coefficients and calculate the marginal likelihood, which is this integral over parameter space, of each model. So that's the evidence of the model given the data. That's the bit that is only possible to calculate when you've got a Bayesian approach. So here are some examples with large measurement noise. So you can see a polynomial with order 1 with large measurement noise. That's the line that fits best through the original points. With order 3, 5, and 7. So 7, we have a wigglier line. On this left plot here, bottom left, we have the polynomial order on the horizontal axis, and then how well that model fits the data. So bad fit down here for polynomial order of 1, very good fit for anything above about 6 to the data. So that's just how well the model fits the data. But then when you penalize models with too many parameters, you get this plot on the right. And you find actually for this measurement noise, the first order polynomial is indeed most likely to have given that data. It's the most probable model to have given that data, given that large measurement noise. And the 9th order polynomial is being very heavily penalized by the fact it's got 10 coefficients. And with those 10 coefficients, with that measurement noise, you still have a lot of uncertainty in those coefficients after you've assimilated the data. So it's not a good model. And that's the bit that even though it's a good data fit, when you account for the fact it's got loads of model parameters, it's heavily penalized in this Bayesian approach. And that's what's so nice about the Bayesian approach. You can flush out these bad models because they have too many parameters. If, however, I now shrink the measurement noise to something tiny, you get this. The data fit, of course, doesn't change. The absolute value changes, but the relatives don't. But now you can see the first order polynomial is being heavily penalized because it doesn't fit the data. And we're very sure about that data, very certain about it. And then here, 5, 6, 7, 8, 9, they're all good models. And you can see that the 6, 7, 8, 9 are being slightly more penalized by the extra model parameters, but that's only very tiny. So what matters, of course, is the measurement noise. And I'm going to change now this little video that increases the measurement noise. And look at the bottom right plot. As you increase the measurement noise, these low order polynomials become more likely given the data. So I can just sort of shoot back and forth, I think. So when I've got very little measurement noise, the higher order polynomials have the most evidence. And as I increase the measurement noise, the low order polynomials do. So that's an example of this Bayesian inference sort of in practice on this polynomial case. Right.
Hi, can I ask a question?
Imagine I just have this, just the points. Humans can say, depending on their experience, are they experimentalists, are they CFD? They put a different line to those points. What are you doing when you do that? You're assuming something about the error. Instinctively, you're assuming something about the error, given those points, from your prior knowledge of these points. So you are, as humans, introducing prior knowledge when you do this. Humans are very good at this game, instinctively. But what you can do with the Bayesian approach is actually say, I don't know what the measurement noise is, but I can let it float, I can let it change to maximize the marginal likelihood, the evidence of each model given the data. So as well as changing the model parameters, I'm also going to let the model, the measurement noise, or the model error and measurement noise float as well. That'll change. And so I'll find the optimal measurement noise or combination of model and measurement noise given that data. So this is for polynomial order 1. Of course, you need a big noise to fit the data. Polynomial of order 7, it fits the points very well. So you want the measurement noise to be very small to maximize the marginal likelihood. The data fit, not terribly relevant. What's really relevant is this. The log, the evidence now, the marginal likelihood for each polynomial given the data. And you find there's one polynomial, 5, which has much more evidence when you let the measurement noise float than all the other ones. And this is a log scale, so that's a lot better. And the nice thing is that that data was created with a 5th order polynomial. I took a 5th order polynomial and added some random noise based on to every point, and then just fed those data points to this algorithm, and it'll point out that the most likely model was indeed a 5th order polynomial. Feels a bit like magic, but humans are very good at this, and you can make a computer very good at this as well. Now, it won't do that every time. This is actually it. I'll just stick this up, and if you want to, there's a tutorial on my website which I made for my first year PhD students. And in order to explain this to them, I think Lloyd, you've done it as well, haven't you? It's quite useful. It's quite fun to play with. If you run that tutorial, you'll get the answers I just shown on there with RNG, the random seed 1. If you take out that line and just run it again and again and again, you'll find it'll get the 5th order polynomial about 2 times in 3. And if you add more data points, of course, it gets it every time. So this is, of course, subject to random error. This doesn't always work every time. But the more data you have, the more information is in the data, and the better this process will get. So I made that tutorial for my PhD students and have found it very useful. Others have found it useful as well. So you're welcome to have a look at it. Right. That was all the theory part. Sorry. Now we're going to do some examples, and it's going to be really nothing but pictures. So everyone likes pictures, don't they? We've done the hard bit. I said I have an experimental rig. This is a rig. This is a tube here, a metal tube. It's about 1 meter long. It's got thermocouples on the outside and then probe microphones. In terms of cost, by the way, tube, about £2.50. Thermocouples, about £2.50. Boxes for the thermocouples, a little bit. Microphones, £5,000 each. So the big tip in life is to buy expensive microphones because they are good. They have small measurement error, small systematic error, and you're really relying on them. So you've got to focus where you put your spend. This is the sort of experimental result we get. So we have a loudspeaker at the bottom here that forces the tube near its resonant frequency. So we build up an oscillation inside the tube, which you can see happening here. This is time on this axis. This is the pressure measured by each microphone, colored for your convenience, a green microphone, a red one, etc. So we turn the loudspeaker on, it reaches a roughly steady state, and then after 1 second, we switch off the loudspeaker and measure the decay rate and the frequency and the relative amplitudes and phases of these microphone pressure measurements. So that's what we're measuring here. And what we're going to see is how that growth rate or decay rate changes as we move this heater through the tube and change its temperature or the power through the heater. And this is a very simple model for a gas turbine engine where you have a flame inside an acoustic network. A very simple model. Yeah.
P6, your last microphone?
So there are 1, 2, 3, 4, 5, 6. So this is 6. There are actually, in this experiment, there are 6. We actually have 8 in the new one I'm about to show. So this green one is the one that is at the end, and then the ones towards the middle of the pink, and there's another one behind the pink one.
Got it. Okay. And yeah.
That. I guess so. Well, they're not normalized here, but we just choose one of them to be a reference microphone. Actually, which one you choose is really important, but I won't dwell on that. And you'd think it should be the one with the biggest amplitude, and that's not a bad guess, but actually it's a little bit more subtle than that. I might say a bit about that towards the end. Anyway, this gets me to how we're going to assimilate the data, and this is this chart you've seen already. So we have some prior estimate of the parameters with some prior certainty. That's a very key green line there, but what we're assimilating is all of these measurements. So growth or decay rate, ZR as measured, and a model prediction, a frequency, and then the relative pressures of the microphones. And this is where we have this enormous loop that's assimilating all this data. But with the gradient-based optimization algorithm, it doesn't take long. It'll take 30 seconds to run this, to optimize and find the model parameters that fit the data the best. This is a chart just showing the number of experiments we do. There are 40 experiments on this table here. And so at each operating point, we do 40 experiments. We simulate all of that data in a few seconds. It's not difficult to do. But maybe I'm going to skip this just to move on. You get interesting. Are there any experimentalists here? A few of you, sort of. Any people who do acoustics? Sort of. So this will ring a bell. What we have is, I'm just going to show one of the many experiments, but this really surprised us. We have this tube, and there's a heater that goes through it, and the heater sits on two prongs. Those two prongs are very long and thin, and they have a sort of thread on them, like this. Now, it is incredibly tempting in your model to neglect the effect of those prongs because they're so thin, and this is a sort of 5 centimeter diameter duct, and you're putting in two prongs like this. Very tempting to say we assume that they're zero. And if you go into the literature, most people assume that the prongs have no effect on the acoustics. But of course, we had to test this. So we put these two prongs through the tube, and these are the experimental results. Look at the black dots. As you move the prongs through the tube, it's called the growth rate, but it's negative. So it's a decay rate of these acoustic oscillations. As you move the prongs through the tube, so over here, the prongs go all the way through the tube, and on the left, they go just into the first bit of the tube. That decay rate is changing quite a lot. It's changing by 2 radians per second, but given that the effect we're trying to measure is about 10 radians per second, we can't neglect this. Now that we sort of expected, because you're actually increasing the acoustic drag, the thermodiffusive drag with these prongs. We weren't expecting this. Look at the black dots again. As you move the prongs through the tube, the frequency, this is in radians per second, goes down and then up and then down again. So the frequency is changing as you move the prongs through the tube. And we can measure this very accurately, at least within 1 radian per second. So we can't neglect this, or if we do, it's a big systematic error or model error, in fact. So we have to put it in to the model. The question is, how do you model it? And if you go to the literature, you'll find all these different ways of modeling things like this. And you can choose as many models as you like. So in the paper we wrote on this, we just chose 3. I labeled them 1 to 7. Perhaps the key thing, though, is the number of parameters in each model. The first 4 include the viscothermal dissipation, and the final 3 include the viscothermal dissipation and also the blockage you get from having 2 prongs in there. The physics is perhaps not so important for this talk, but you can see which models fit the data best. And when you've got positive numbers, that means a good data fit. So model 4 fits the data very well, as do model 6 and 7. But actually, when you work out the marginal likelihood, the evidence, if you like, for each model given the data, you find model 6 has the highest marginal likelihood simply because it's fitting the data really quite well with just 2 parameters, instead of model 7, which has 3 parameters, and model 4, which has 4 parameters. And so you choose model 6. Now, this process, of course, it may not be the best model. There may well be a better one. But given the evidence we have, which is just, in this case, 80 data points, this is the model that fits the data given the, this is the model with most evidence given those 80 data points. And there's no limit to the number of models you can assume, you can test out. But anyway, we do this then, we assimilate the data in sequence, always trying to sort of get this model parameter, the first ones, and the second one, and the third one, and the fourth one, until eventually we've assimilated, in this case, about 15 parameters that describes this physics-based experiment. So this process takes, you have to do it very carefully, but I'm just going to jump all the way through to the end. What you get at the end is, this is heater power and heater position, and this is the growth rate of oscillations, and this is the frequency. And the model is in red circles and the experiment in blue dots. what we get at the end of this very careful assimilation process is a model that can match the experiments really very, very well with very small uncertainty with 15 parameters. And the lovely thing about this model is that it can extrapolate in directions in which the physics remains the same. So if the physics remains the same, you can extrapolate away from the measurements. And once you've chosen the model, it takes very little data to train it. So it actually takes a lot of data to differentiate between different models. But once you said that's the model that fits the data the best, you can then train another model with the same physics with a handful of data points, because you just need to get those 15 parameters. It's another real reason why having high quality prior information is the key to extracting information from data, which is what we're doing here. Right, now, of course, you then say, well, let's think about that Gaussian assumption. We've assumed that all posterior probability distributions are Gaussian, or the data likelihood is Gaussian. And we can test that using a standard technique like Markov chain Monte Carlo or Hamiltonian Monte Carlo. And this is actually some experiments. These are posterior probability distributions calculated with Markov chain Monte Carlo. This, by the way, took about 2 weeks on a workstation, whereas what I just showed you before was a few seconds on a laptop. Very different order of magnitude in terms of cost. This is actually what we did first before we did the adjoint implementation. But nonetheless, you have to look at these posterior probability distributions and say, are they Gaussian? And they are really pretty good approximations to Gaussian. Perhaps you could point out that one's a slightly sort of swoopy, a Nike swoosh type Gaussian, this one too. But approximating these by a Gaussian is not a bad approximation, and it's enabled a speed up of roughly a factor of 1,000,000. So it's really worth doing, and you can check it afterwards. And that's the adjoint acceleration. Okay. I've just got some more pictures now. I'll carry on. I'm aiming to finish in around 12 minutes. Is that okay? All right. So Bayesian design, this is, I'll just do this very, very, very quickly. If you're interested, we can talk later. This is a sort of cartoon of a parameter, single parameter, and the probability distribution before assimilating data and afterwards. And you can work out what they call entropy in the information world, or think of it as the information content of the next experimental data point. You can say, what's the expected value of the change in entropy or the information content of a new data point, even though I haven't done it yet. Once you have a model with some prior information, usually in the form of previous data, you can then say, if I were to do an experimental data point here, or so I rephrase that, where should I do the next experimental data point to get as much information as possible for that particular model? Now that works really well. And here's an example of that working for this Rika tube. So we have the heater here on a moving up and down through the tube. So this is the heater position in the tube here. And this is the growth rate, and this is the frequency. These are the measurements with measurement uncertainties shown here. What I'll do now is I'll give a model with some really loose priors. I'll say, I don't know much. I know the model, but I don't know what the parameters are of that model. So this is the model prediction in dark blue, but with very, very big uncertainties, so big that they don't fit on the chart. And what I'll do now is train that model on the data. Now, what I'll do is say, given that model, where should I put the first data point? And so this is the information content you get from a data point at a different heater position. And you can see that putting a heater at 0.5, which is in the middle of the tube, contains the most information given that model. So that model is hungry for a data point at 0.5. So we feed it the data at 0.5. And now you can see the certainty collapsing to the experimental certainty at the data point I fed it. But because this model contains it contains a presumption about how this experiment will behave away from that point, you can see it's also collapsed the uncertainties around that data point. And now we look down here at the expected information from another data point, and it's saying it's hungry, it really wants a data point at either the left-hand end or the right-hand end. So we'll feed it data point there. Oops, there we go. And now we fed it that data point. And firstly, you can see by eye that the model has collapsed to the experimental uncertainty. But this is the key thing. If we look at now the extra information we'll get from another data point, it's almost zero. There's no point doing any more. If you look really carefully, by the way, you'll see that the model has got a bit too confident. And that's a common feature of this process. Models, they don't know what they don't know, just a bit like humans. There's a great line from Peter Pan, "I'm not young enough to know everything." And when teaching undergraduates, that's an often something that comes to mind, even if I don't actually say it to them. And models are a bit like that. So, but the point is this, that you're able to train this model with 2 data points, well-chosen data points. Now that works if you know what the model is before you start. If you don't know what the model is, you can't do this. You can, anyway. Right, I'm now going to switch to the changing tack, neural networks. So this is very popular at the moment. Physics-informed neural networks. I had a postdoc who worked with me for 2.5 years doing this, and they work. They're fine, but they're not the best solution for this problem anyway. They're definitely not the best solution. But I'll just show you what we did. And I put this up. I'm always nervous when saying physics-informed neural network because I found that people tend to focus on this. And at the end of the talk, they'll say, well, what were the parameters? How many layers did you use? How many neurons in each? And I go, well, no, the whole talk was to say I didn't use a neural network. But sometimes they miss that. So I'm saying that explicitly. This is a project we did with a physics-informed neural network. And I'm showing it to show you why it wouldn't be the best solution for this problem. And then why the best solution is the CFD that I'll show later. So a physics-informed neural network, as I'm sure you know, you take a neural network with some inputs and some outputs, and you penalize it if it doesn't match the Navier-Stokes equations in this particular case. And then what you do is we say, I've got some raw data. I want to reconstruct a flow. That is to say, I want to find some sort of CFD solution or CFD-like solution that matches that data while also matching the equations of motion. So I penalize my neural network if the raw data doesn't match the reconstruction from the neural network doesn't match the data. And I also penalize the neural network if it violates the equations of motion, Navier-Stokes in this case. Now, that works, and you'll get accuracy with the neural network of around 10 to the minus 3 on a scale from 0 to 1. But what we do instead is we don't do this. We replace that neural network with a CFD solution where we've hardwired the equations of motion into that CFD solution. This is a finite element, so we can converge to 10 to the minus 12 accuracy. In fact, you have to do the data assimilation. And what we do is we say, what I'm about to show you, actually, I'll talk about this later, but the main point I want you to take away is that we've replaced this neural network with 1 million parameters with a CFD problem with 10,000 parameters. And the fluids is hardwired, the physics is hardwired into this model. It's not floppy, it's really hardwired in. It's a much more satisfactory way, I think, of assimilating data. You assimilate the data directly into a physics-based model where the physics is hardwired into the model instead of into a neural network where you have 2 soft constraints. One is how well the data fits the model, and the other is how well the equations of motion are satisfied. So that's what we do next. Right. I'm now going to go back to this. I'm glad you asked me that question, Sam, because here they are. These are the parameters. So what are the parameters, asks Sam? It's the key question. Yeah. So this is a 2D representation of a 3D CFD solution. So I say I've got some domain I, which is, as I'm showing it here in R squared, in 3D it would be R cubed. I'm going to look at some magnetic resonance imaging data. MRI data, it's the cleverest thing you've ever seen, MRI. And it gives you really high quality data. You get 3 components of velocity in 3 dimensions and 1 in time. So you have a complete view of the flow, usually flow going through a tube. And it's very, very high quality data, but it comes with lots of measurement noise. So what we do now is we take that very high quality data, high quality meaning it has a lot of information in it, and we add some very high quality priors. And the very high quality prior is that we're looking at, I'll show in a minute, the flow through an aorta, a human aorta, 3D printed. We know that that image is of flow going through a tube, but this is the parameters. We don't know the position of the walls of that tube, and we don't know the inlet velocity profile. So we say within this domain, we know the domain we're looking at, we know that there is a boundary gamma, but we don't know where that boundary is. And so we're going to move the boundary around. And within that boundary gamma, the flow obeys Navier-Stokes equations. So continuity of mass, continuity of momentum, or conservation of momentum. And so we change the inlet velocity profile and the boundary position until this CFD solution best matches the data. And we have a pressure outlet here, a zero stress outlet here. So the parameters actually are in defining the shape. And that's where most of the parameters sit. There's parameters defining the inlet velocity profile. And there's one more parameter, which is the viscosity. This is a Newtonian fluid. You can, by the way, look at different types of fluids, but you have to model them with different parameters. So this is just Newtonian with a viscosity that we don't know. So that's what we do. And then what we do is we say, we've got some data here that's noisy data from MRI. This is just synthetic data to show you what we're doing. We find the simulation by moving the walls and by changing the inlet velocity profile. We find the simulation that is as close as possible to that data. We do that using adjoints. So this is a relatively cheap calculation, even though it's got many, many parameters. And then in this case, you take the difference between the two and we get the noisy noise here. But in this case, this is the noise we'd added to this simulation to get the data, and then we trained on that data or assimilated that data. And here's an example. This is, I don't think you can see this very well, but this was done for our JFM paper because one of the reviewers insisted that we did a biologically relevant flow. And we sort of, because, you know, this is a 2D aorta. Such a thing doesn't exist, but nonetheless, it's got a roughly sort of, I haven't shown the boundaries, but the flow is moving fast around here. And crucially here, we have this sort of recirculating zone here where the flow is moving smoothly. This is a 2D aneurysm in the 2D aorta. Now, aneurysms are very bad for you, by the way. If they burst, they kill you. So, but when you add some Gaussian noise to that data, the velocity field, you get this flow here, and this is typically what an image would look like. And can you see that recirculating zone? You can't really see it. A human can't see it. But if you say to a computer, what is the boundary position and the velocity profile most consistent with this noisy image, it gives you this. And you can see it's found that recirculation zone, because in order to satisfy conservation of mass and momentum, it needed that recirculation zone. And I haven't shown the boundaries explicitly, but you can sort of see where they are by the streamlines here. So that's so that's what we've done. And if we compare the reconstruction with the ground truth, hard for you to see there, but they're very similar. You could perhaps quibble that the recirculation zone here isn't quite the same as it was in the ground truth, which is here, very slightly different. But that's because this data was corrupted by the noise. So you can't actually extract all that information back, even with these very high quality priors. You also get the pressure distribution and the wall shear stresses. I'll skip over that, and maybe I'll skip over that bit too. And we were stunned by this criticism that we couldn't look at complex geometry. So this is what we did now, was take an MRI of a drain pipe filled with marbles and a flow going through it. And this is assimilated on a laptop, simulating the 3D flow around it. You know, we can do very complicated geometries with this method because we've designed it to do complex geometries. So we started here and said, we don't know what the flow looks like. We don't know what the boundary looks like, but you can assimilate the boundary from the data because it's such high quality data when you put in that very high quality prior as well. Right. And I'm going to finish now with some really pretty pictures. So what I just showed you was in 2D. The last thing was 3D, obviously. We're obviously aiming at doing this in humans, but before we do that, the medics say, well, what about the ground truth? We need the ground truth. And you realize that medics whisper it. By ground truth, they mean CFD. And it's just, it makes you just, anyway. Because, of course, ground truth is what's inside the human, and you just can't see it. And no amount of CFD can make you see it. So what we're doing instead is we're 3D printing a human aorta, life-size aorta, and then looking at firstly steady flow, then pulsatile flow, and then eventually we'll do this with walls that move as well. But we had to do this slowly because we're building up the sort of evidence for it to actually work. Sorry, this is the last few pictures. So this is a 3D printed aorta. This is typical of the sort of data you get, very good data from MRI. This is a slice through the 3D velocity field, vertical as we see it, horizontal, and then coming out of the page. That's really good data from MRI. And that was a week in the thing. And this is the assimilation process. The red is the big discrepancy. The blue is the little discrepancy. We're assimilating the data now directly into our CFD solution. There's not a neural network in sight. Do you remember that? No neural networks. This is directly into CFD. And at the end, you end up with, you can't see it very well here, but you have this irreducible error between the CFD and the measurements that just it could be model error, it could be measurement error, we don't know. There's always a discrepancy between the two at the end, but nonetheless, you found the most likely shape. So if this was the original shape, this is the shape that we assimilate just from the velocity field. So the velocity field, of course, contains a lot of information about where the boundaries are because of the zero slip condition. So that's the assimilated boundary. This was the vertical velocity. After assimilating the data, you get a lovely smooth velocity field that matches Navier-Stokes and continuity. This is the horizontal velocity. It's, again, quite hard to see on the screen. This is my favorite, the through plane. So coming out of the plane, you're not quite sure what's going on just here, really. But when you say what's most consistent with Navier-Stokes, you get a really crisp picture of what the flow looks like. And you also get the pressure field. And I think the most important thing is this, the wall shear stress. You get a very accurate wall shear stress, which is what the medics really want, because they think wall shear stress may be the cause of disease in arteries. And I'm going to finish with a bit more philosophy. This is Enrico Fermi. I remember my friend Johnny von Neumann used to say, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. And I write that because every time we put in this Bayesian inference into models with many parameters, one of the reviewers comes back with that quote, sometimes fatally, for the paper. And it really annoys me. Because we are used to these days, we're becoming used to assimilating data into models with millions of parameters with no physics at all and saying that's fine. What I'm proposing is to take the same data and assimilate it directly into these physics-based models with known parameters. And that feels much more satisfying, even if there are many parameters, than these physics agnostic neural networks. So the sort of what I'm really trying to say, take away all of it, is this: put the physics in the model if you can. You can't always put the physics in the model, but if you can, I think you should hardwire it directly into the model, assimilate into that model, and that process is far more satisfying than going into neural networks. And you do that with Bayesian inference. And I'll stop there. Thank you very much for inviting me, or at least letting me talk. Oh,
Thank you for a wonderful talk.
don't know where to finish. I'll do.
I will catch you.
We'll catch you later. Yeah.
Okay, I have so many questions. But my first and foremost is that as an experimentalist, we are working on DVD for jets, hydrodynamic jets.
Right.
So we've got high voltage electrodes with a dielectric, and then you're gonna ionize your air, and we're working on AC applied voltages. You have, we basically narrowed it down to 4 phases. You're like negative, positive going voltage, you're positive, positive going, and so forth. And so we're trying to make a physics-based model to represent the thrust and the flow fields and whatnot. And I'm looking at, especially when you were doing the example with the polynomials. This seems like a really interesting way to analyze the efficacy of our models that we've made. Is that kind of my ignorance, or would you agree with that and think this is a good way to?
I think this is the best way to do everything. So yes, obviously. So you're starting from some physics, and you're starting from a physics-based model.
We're trying to find the physics.
Is this with a Cindy type approach?
What?
With a Cindy type approach? Or, yeah. I didn't mention it, but Lloyd, of course, I don't know if you saw Lloyd's practice talk.
I did not.
No. So we, in fact, Lloyd over the summer, all Lloyd's did all of it, was using the essentially Bayesian approach to Cindy. So doing Cindy from a Bayesian perspective. And I think it's worked pretty well. I'm totally biased.
They're limited. We're running off of Keto 2 right now.
So that's where Bayesian version of Cindy that present simplified in will make sense.
Yeah.
It works really well with data regimes that's very noisy or not enough data. Right. Cindy struggle. That's what we like to do. Yeah, okay.
Yeah. I mean, over the summer, I haven't seen it for a while. Over the summer, it looked really good.
Wow.
But it still looks good. I think what Lloyd said, the main point to take away is that if you have noisy or sparse data, this Bayesian approach is brilliant. Because it's essentially, because you introduce a model the model will be somewhat smoothing, or it gives you a way to interpolate between data points with rigorous uncertainty. And I think that I didn't mention it, but the book that I took most of this from was David Mackay's book on information theory, if anyone's come across that. It's a very hard read, but it's also the only read you need to do. So David Mackay, Mackay, information theory. He did another very good book on sustainable energy. It's not that one, it's the information theory. Where was I going with this? That contains all of the sort of, yes, you've got to think in terms of information when you've got data from experiments. And you have a prior space that when you prior uncertainty in parameters, that collapses when you introduce the data. And that's a sort of key way to think about it. So when you have just a few data points, there's not very much information in there until you introduce the prior model. And then suddenly you can extract lots of information from that data. That's the way to think about this. And if you're comparing models, if they're completely wildly different from each other, then just a little bit of data will be enough. If they're quite similar to each other, that's when you need a lot of data.
Okay. Well, it sounds like I need to talk to Lloyd.
Yeah. I'm here all day, so we can talk as well. Yeah.
Couple of questions, really nice stuff, by the way. If you go back to your slide with the Jacobians, the Jacobian of the partial J, partial A.
Yeah.
And the first order, or the second order one too. So I'm all in on this idea of using the business models, using the agile and stuff of business models. My approach has typically been using automatic differentiation and putting up the simulator itself. So I'm curious, is that something you're doing, or are you constructing the agile analytically?
Such a good question. This is a really important technical question. So the concepts we've done, and then you say, okay, so conceptually, we know what to do, but what we really want is technically to get the derivative of the model output with respect to the parameters. Now, you'll know, but many people won't, about the difference between discretize, then adjointize, and adjoint, then discretize. And this is like, I often liken it very riskily. Are we still being recorded? Oh dear, I've got to be careful. I once at APS was asked this, and I said in front of everybody in the big hall. It was my big talk in 2019 or so, 2017, I think. I said, I was standing next to Colm, who I know and like very well. Colm is Catholic, I guess I'm Protestant. Colm's from Northern Ireland, so there's a sort of history there. And I said, it's a bit like Christianity. You've got the Catholics and the Protestants, and it's all the same religion, but they'd still like to fight each other. And I feel it's a little bit like this, with this discretize, then adjointize, then adjoint, then discretize. But it's all the same thing. But actually, there are some very important technical differences. I put it like this. Automatic differentiation, or discretize, then adjointize, is easier to do. Adjoint, then discretize is harder to do, but is better. So a very good article is Andrew Stewart's 2010 paper, which we can talk later, and I'll show you what it is. He's a big advocate for do everything in continuous space and then discretize, and it is better than working in discretized space. Now, it's very subtle as to why that is, but if you work in continuous space and pay great attention to the function spaces you're using, you can then when you discretize, you use exactly the sort of smallest discretization possible for that problem, so the fewer number of parameters. Whereas if you start in discrete space, you write your problem in discrete space, often you'll have too many parameters, you'll have discretized too much, more than you need to, and you've got to pay real attention to the boundary conditions, because you won't realize that when you do a forward solver, you sometimes introduce boundary conditions with arbitrary parameters that you usually set to 0. And the adjoint solution doesn't know that. So you find yourself with problems, you get oscillations of the boundary because of a bad boundary condition that doesn't make any difference to the forward problem and kills your reverse problem. And you don't know it, because why would you? I mean, you've written forward codes as much as you like. So I found, from personal experience, if you can write in continuous space and then discretize at the end, that's much better. But if you're just writing a code, a forward code, you need to know you're going to take the reverse code later when you're writing the forward code. And so you then, even if you're using automatic differentiation, you need to know, you need to make your problem easy to differentiate. Yeah. And if you don't, you're in real trouble.
And you're in real trouble often.
You're in real trouble. It's if you basically, and I've done this at the beginning in 2006 with Peter Schmidt, you take somebody's code and say, oh, I'll just write the adjoint of that code. How hard can it be? And that's just the naive approach, because it's really hard.
Yeah.
And the best thing is often to throw away the code you've been given and write it again.
So
Yeah.
is that what you did in your last part? With this
Yeah, well, I didn't do it. Alexandros did it. So he completely rewrote finite element code with a moving boundary. That problem is hard because of the moving boundary.
Yeah,
and you
that's
need-
your free parameter.
Yeah,
That was the movie.
yeah. But he was very careful about the function spaces he used to solve that problem. And so what I showed there, it actually ran on a workstation, but it could run on a laptop, that assimilation problem. At APS last year, I presented that work. And I remember someone saying at the end, okay, so what cluster did you use? How much power did you use for that? And I said, no, everything I showed here was on the laptop.
How
No.
big was that? In 3D and then some number of time steps?
Yeah, it was about 40 time steps.
And how many an XML is it?
How many?
How many?
Oh, 100 by 100 by 100. It's really quick. I mean, it's not trivial, but it's a day maybe on a laptop, much faster on a HPC. But the point is, it's completely accessible in terms of computing power. Whereas neural networks doing the same thing require GPUs at a much bigger scale. What we're doing right now is trying to make this work on GPUs, because I think that'll be lightning fast. And the nice thing about neural networks is they can piggyback on the hardware acceleration that we can't at the moment piggyback on. But I think if we can combine that with GPUs, this will be very, very quick. My goal is to put someone in a scanner for one breath hold, 15 seconds, and then process the data within an hour. That would be the goal. Because at the moment, to get enough information from the data in MRI, you've got to put someone in a scanner for 90 minutes. They have to hold their breath for 15 seconds, let it out, hold their breath 15 seconds. Every time they move, of course, you've lost a bit of focus. But if you can just replace that with a 15-second scan and then a 1 hour process, your problem becomes how many people can you get through the scanner, not how much can you use your scanner.
For your 3D printed aorta, did you use water or did you use a shear thinning fluid like?
That was actually a mixture of water and glycerol. So it was a Newtonian fluid, very deliberately, because we didn't want to deal with a non-Newtonian fluid.
Do you have any idea how much more it's going to complicate it when you have to back out some sort of?
That's a good question. We did this over the summer in a different configuration, just a nozzle. We looked at I forget what type of fluid it was. It was a non-Newtonian fluid. And then this is a sort of scoping study. We took the 20 viscosity models. We just over the summer selected one and assimilated the data into that model. It worked really well. What we wanted to do was do that for all the different models and select the best model. It almost became a trivial task because of all those 20 models, there was that one that had like 2 parameters, and some of the others contained whole, 9, 10 parameters, and you could tell that these parameters were almost canceling each other out, that there was no way that data could distinguish those 9 parameters. So I just find what we took away was that these viscosity models seem to contain vast numbers of parameters, some of them which are superfluous. So I don't know, this was a scoping study, and I think the plan is to write it up and then make a publication out of it. I don't quite know when that's going to happen, but you can do it. Yeah, you just have to assimilate data into the viscosity model. And for that simple model, it worked really well. But for these complex models, you just can't assimilate all those parameters.
Did you do that at the same time as you were
And the velocity field.
moving the boundaries?
Yes. Yeah. So you basically move the boundaries, change the inlet profile, but also change the parameters of the viscosity model. It works fine. So for blood, you'd say we know how blood behaves. You'd introduce some prior and assimilate into those. The nice thing about the aorta is that at that scale, the blood really is quite Newtonian. It's only when you get to these very small scales that it becomes less Newtonian.
So back to the computation on a GPU. Is there a particular implementation bottleneck you're facing? As a lot of this is just matrix, math.
The bottleneck we're facing right now is purchasing a GPU. So there's no, as far as we're aware, bottleneck. but we'll see. So this is we at Cambridge have an HPC, a high performance computer with GPUs, and we could, I think, develop on those. But I've always found with CPUs anyway, it's best to have one in the office that you just have permanent access to debug.
I think it would be interesting to just get like a 1060 for $150, and see how it runs on that really consumer grade.
Maybe let's talk later, because I think we're facing that question right now. Yeah.
Because you're still gonna have way more cores. Like,
Sure.
you're gonna have way higher core count to work with.
Yeah.
Even with that really cheap consumer core.
So
On the aorta, were you able to check the Gaussian assumptions?
I didn't show the uncertainties of this. No, that's too expensive. I mean, for these sort of the 2D toy problems, yes, you can.
Because that would be perfect.
Yes, so funny enough, the uncertainties become quite tricky because we want the uncertainties of the model output with respect to the parameters. I mean, we can get the uncertainty in the parameters that's fine. To get the wall position, that's an uncertainty you can get quite cheaply and then plot. So we have uncertainties in the wall position. If you want to get the uncertainty in the velocity field, that's an expensive calculation. So we don't really do that. We haven't done Markov chain Monte Carlo on that problem. That would be really quite expensive.
You need some fast statistical tool that allows you to verify the Gaussian assumption.
I guess we would, yeah. So with that, I guess that's the sort of out of scope for this study is what you write in a paper, isn't it? When you just can't be bothered to do it. Yeah, left for somebody else. Yeah, and the nice thing about MRI is that the noise is Gaussian, the measurement noise is Gaussian, and the for this flow, we deliberately chose a laminar flow because we didn't want to deal with turbulence. There's a whole new question about how to deal with turbulence in. Oh, cripes! One thing at a time. Yeah.
And that can be really in trouble.
For your the model selection problem, I think I missed how it sounded like you were also scanning, or you had a free parameter in the amount of noise measurement error you had experimented. How did you? But then you said you also fit that. You fit.
Yeah.
What? I think I missed how that.
So in terms of how, take here for example. This is the measurement noise, CEE. You can get the cost function, dj, by the measurement noise. So you calculate it like that. And there's also pre-exponential factor here that contains that measurement noise as well. So you just do the derivative of j with respect to the. Yeah. It's actually the easiest thing to do.
Per model type that you have. And then you have some value for each model.
So because, and this is the point made earlier, that actually this measurement noise also contains a model error.
Right.
We let this float as well when assimilating the data. And then you say for this model, in fact, it's exactly like the polynomial problem. No, for this, sorry, where was it?
Yeah, that's
There we go. For this model, the polynomial order one, that's the optimum noise. And you can imagine doing that with actual physics-based models. And I think I found that the fairest way to compare models against each other. Because, of course, if you say that uncertainty is tiny, you're never going to fit a simple model to the data. You have to allow the model error / measurement noise to float. And the real question, by the way, is how you choose the priors for that. But that's another question. I'm aware that some of you might have to go. If you have to go, feel free to go. I'm very happy to talk for as long as I talk, but if you have to go, don't feel you shouldn't. Sam?
I have a question about this example actually. So you said that you introduced a penalty for higher order polynomials. Is that something that just comes out of the Bayesian?
It is, yes. It just drops out through. Here we go. This matrix here. So remember that matrix is the posterior uncertainty in the parameters. Now it's actually quite subtle. So what you naively think is that I want my parameter space to collapse to a point. Meaning that I've 10 parameters in a ninth order polynomial. I fit the data and it collapses to real certainty in those parameters. That's actually not the best model. What you really want is a model that can fit the data even if the parameters change a bit. And that's your best model. So here, this determinant of the matrix here is a little bit subtle, but that for the ninth order polynomial, which collapses to a point, I hope I get this right now. The evidence, and maybe you can sort of see two directions here. In one case, there's this sort of parameter space collapsing to a point, and you end up now with a model that's really, really sort of delicate. On the other hand, you can have a model whose parameters don't collapse at all, and then you've learned nothing from the data. That's also bad. What you want is something in the middle, and that it's quite a subtle point, and I'm manifestly not very good at explaining it right now. But the best thing is to look at this. You can look at these two. This is called the data fit. This is called the Occam factor, and there's a trade-off between the two. I think I will stop embarrassing myself by not answering more of that question. But I mean, we're not the only ones to have trouble describing that. But I think if you think about the ninth order polynomial, you sort of instinctively know what I mean, which is that you can tune those parameters exactly, but that model is now very delicate. All right, should we stop there? Thank you for coming. Very nice to be here.